This is Practical Python Programming for Everyone, Lesson 3, and the topics for this session are strings revisited and loops. You can follow along with the presentation by visiting this link here, mco.fyi/py3. I'll show you what that looks like when you click on it or visit the URL. You end up in a notebook, Colab notebook. What you'll want to do is make a copy of it. So go ahead and do File, Save a Copy in Drive. You'll get your own private copy of my notebook. The title will be Copy of my notebook's name. You can change that freely by just clicking up in the upper left and editing that text. But this is your own private copy, and so now in any of the code cells you can actually modify things and do whatever you want, and it won't affect my copy. So back to the original file. I'm just going to start walking through these cells. Now you might wonder, why are we doing so much with strings? We've already spent a lot of time on strings. Don't we know enough? Can't we move on? And the answer is yes, we could, but there's some things about strings that I want to cover that apply to more than just strings. They in fact apply to all class of data types in Python called sequences. And we'll learn more about sequences. The specific types that you'll learn in those modules are lists, tuples, and dictionaries. And you'll see how they work. But pretty much everything we cover in strings today will apply equally to other sequences, and that's why these are important to understand. So let's start with the len function. Len is short for length, and it returns the length of a passed string. Here's a few examples. There's a code cell here you can try yourself. So len of 2b or not 2b, if you add up all those characters in that string, including the spaces, should be, I think, 18. I'm waiting for the notebook's back end to warm up. So yeah, it's 18. If you add a new line character, it's 19. And the thing to realize there is that the \n is a way to express a single character, which is the end of line or new line character. So that is expressed with two characters, the \, and the n, but internally it gets represented by Python as one character, and that's why the count or the length of that string only went up by 1 from 18 to 19. If we throw away the white space and kind of crunch it all together, we get a 13 character string. And if we use an empty string, we get a length of 0, which makes sense. Another important thing you can do with strings is index them. And what that means is refer to a character somewhere in the middle of a string. Actually, it can be at the beginning or the end or the middle, but it's the key idea is you want to sort of peek into a string and access some component character in that string. Indexing works with both variables and literals, and I'll show you examples of those in a second. But a key thing to know is that in Python, the offset that we use in this expression, string, and then in square brackets, offset, the offset is a numeric value, and it always starts counting at 0. So the first position in the string, the first character in the string is offset 0. Let's look at an example. So here's a string called Meister, and it's set to mark. If I print the 0th character, that's going to be this leading M here. Let's run this code. The first output, the Meister 0, is the M, which is the 0th position in the string. The position 1 or offset 1 is the second character, A. We see that here. If we jump to position 3, the way I look at this is 0, 1, 2, 3. It's the C at the end of the string. One way to access the last character in a string without having to know how big the string is to combine the length function, the len function that we just saw, with indexing. So I can say Meister index len Meister -1. Now why do I have the -1 there? Why don't I just say index of len Meister? Well, the reason is because of that starting with 0 thing. Kind of throws everything off by 1. If you think about it, a 4-character string is, you don't want to take that 4, the length of the string, and try to use that as an offset, because as we saw earlier, this is 0, 1. Whoops, didn't mean to do that. 1, the A is 1, the R is 2, the C is 3. So position 4 is sort of off the end of the string and would actually cause an error. So what the convention we normally use is for indexing the last character of the string is len of string, and that can be any name I want, but in this case it's Meister, minus 1 to convert it to an offset. And when we do that, we get the last character of the string, which in this case is the C. Just to show you that works for any size string, I'm going to comment out, or string out if you will, these 3 prints because actually they will work. I was going to say they might not work, but they will work just fine. Let's leave them in. Meister of 0 is still M, 1 is still A, 3 is still C, but now the len of Meister minus 1 is the very last character, N. So that's showing you that this works independently of the length of the string I use it with. This example shows that we can do indexing on a literal string. We don't have to use a variable. So here I'm saying take the second offset, M is 0, 1 is, A is 1, and R is 2. So the second offset would be the R, and we see it, that's what we get. And the key here is that we're applying the index to a literal value, not a variable. And I think this is probably overkill, but Meister 4 is 0, 1, 2, 0, 1, 2, 3, 4. It's this C right here. Now, if we go back to the original definition with just mark, and we try to access Meister 4, that sort of falls off the end of the string, and we should get an error. And sure enough, we do. And Python gives a pretty helpful error message here. It says string index out of range. So that's telling us, okay, we better look at our index and figure out why it's not a legal offset into this string. One more thing I wanted to tell you about is there's a convention where you can use negative numbers in the offset of a string index. And let me start with a simpler case of minus 1. Minus 1 is defined as the last character in the string. And then minus 2 is the second last character in the string. So this should be R. Minus 3 and so on, this should be A, and minus 4 would be the M at the beginning. And so this is an easier way to refer to the sort of end characters in the string. It's often useful in loops, and if you want to use this as a shorthand, it's certainly simpler than the syntax here where we have to do len of Meister minus 1. So feel free to use that convention as well. Next up is slicing. And slicing is a lot like indexing, but it's a way to request more than one contiguous characters from a string. And actually you can request one character as well, but it gives you the flexibility of, whereas an index with a single offset gives you one character only, using this notation with a beginning offset, colon, and then an ending offset gives you the ability to access actually 0, 1, or more characters. So it's a bit more flexible. The slice always starts from offset BEG in this case, which is the first numerical value in the specification, and then there's a colon, and then it goes through to the end value minus 1. So once again, we see that pattern of end minus 1, everything up to but not including the last offset. This can be very confusing, and I guarantee will cause you problems at some point in your code. But it's good to try to understand this and wrap your head around the idea that the general rule for specifying a range in Python, and it actually applies in many programming languages, is the beginning value as an offset starting with 0, all the way up to, but not including, the end value. So up to the one less than the end offset. Let's look at an example. We have Python is cool and a string here, and we want 0 through 6, 0 colon 6. So we start with 0, that's the P at the beginning, 1, 2, 3, 4, 5, and we stop there because we want to go to one less than the ending value. So the 6, which is a space, is not going to be part of this slice. Let's actually run that cell down here. And what I don't like about this example is you can't really tell if it included this character or not. Because it's a blank or a space, it could be there and we can't see it. So I'm going to do something here just to make sure that it's clear. I'm going to put an X there. And we'll see that we get Python without the X here. And in fact, if I went 0 through 7, I should see the X, which I do. Okay, let's revert back to the space. 10 through 11, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is the C, and through 11 is up to the offset 11 minus 1, which is 10, so it's 10 to 10. Should just be the C, and that's what we get. And of course, a simpler way to say this would just be Meister of 10. There's no real reason to use a slice here, but I just wanted you to know that that's valid syntax. 10 to 10 would say go from offset 10 to 1 less than the end, which 10 minus 1 would be 9. So 10 through 9, which doesn't really make sense, so that's an empty string, and we see that there's a blank line here. Same with 10 through 9, same story. This last example says take the string math is cool and slice it from 1 through 3. So that says offset 1 all the way up to including offset 2, which is 1 less than 3. So we're going to skip 0 because we're starting with 1. Then we're going to pick up the A and we're going to go to offset 2, which is the T, and then we're going to stop because we're not going up to offset 3. So we get AT, and the key thing I wanted you to understand about this is that I'm doing slicing not on a variable but on a literal string value, which is perfectly legal. There's some defaults to know about when you do slicing. You can leave out the beginning part or the end part. So if Python sees a colon and nothing before the colon, it assumes a beginning of 0. And if it sees a colon and nothing after the colon, it assumes len of the string minus 1. So the last character in the string. So the way I think about this is if you don't put the number before the colon, it tells Python start at the beginning. If you don't put a number after the colon, it says go all the way to the end of the string. And if you don't do either, it says I want the whole string. So I'm not even going to walk through this example because I think it's pretty straightforward. But if it's not clear, I suggest running this cell and playing around with the numbers. And this is a sort of a general rule for these notebooks in general. If you're fuzzy about anything at all, just do some experimentation. Just follow your curiosity and see what happens when you change the code here. And that's one of the cool things about these notebooks. Here's a challenge for you. I'd like you to see if you can predict the output from the following print statements. So I've got a mixture of indexing, I've got the len function thrown in, I've got slices, got some weird slices. So take a look at these and maybe just jot down on a piece of paper what you expect the output of each one to be, and then open this cell and run it and see what you get. I think this is left over from an explanation, but anyway, I'll let you try that. Next up is the in operator, in. In is a Boolean operator, and it's really a test of whether a given string is contained in another string. So it's not just saying is a character in a given string, it's is a string in another string. And the string could be a single character, it could even be an empty string, but oftentimes it's 2 or more characters. But it's testing for existence of one string inside another, and that's why it's called in. The result is a Boolean value, either true or false. And examples would be the character A is in mark, so this should be true. The string ARC is also in mark, that's also true. The string M, just one character, lowercase m, is not in mark because in strings we know that case matters, and this is a lowercase m, and that's an uppercase m, so that should be false. The string mark is in mark, so strings are proper subsets of themselves. Every string contains themselves. The string X contains string X, so that's going to be true. And then the empty string is actually considered to be part of every string, so that will be true. That's a little bit weird, but it's just one of those rules to know about, that every string contains the empty string. And it makes sense if you think about it. You could reduce this string as much as you want all the way down to the empty string. So to review, we said this one would be true, true, false, true, true. So all true but the middle one. And let's verify that. So that checks out. There's also something called string methods. And I realize that, we've been calling things, and sometimes we'll say that's a function call or a function, and sometimes we'll say that's a method call or a method, and that can be a little bit confusing. So it's important to understand the difference. The way I like to think about it is whenever you call something and it's sort of independent of the thing you're operating on, like the string or the number or whatever it is, if it's independent of that, then we call it a function. If the thing you're calling is related to the data that you're operating on, then we call it a method. This will become a lot more clear when we start to understand what objects are and how objects are created. But for now, I'm just going to give you some examples, which I hope will help. So let's actually start with a function. So we've got a variable name, and we're setting that to the string Mark Cohen. And then I'm going to call a function len. And I have to pass len the variable or the literal that I want to get the length of. And so it's not really like the length, task or capability is tied to that string in any way. It's just a general thing that I can ask Python to do for me. And so we would call length a function. We get this kind of weird stuff at the end because I turned these into a string to avoid running them. But the key output is here, this 10. So len is a function. Now we could also say I want to get the uppercase version of my string. And the way to do that is there's not a function upper that I pass name, at least not that I know of. Let's see if I get an error when I do that. Yeah, it says, no, that's a different error. That's because I had misquoted that string. Yeah, so name upper is not defined. There's not a function named upper. I could create one, but there is something called a method, and it's it's kind of connected with the string data type. And to invoke it, I say name, the variable containing the string, dot upper. So the name dot is saying upper is kind of a part of the string. And that's really the essence of what makes something a method. It's tightly associated with the piece of data itself. So if I have a variable that points to two different types or two different pieces of data, the upper method might do different things for that. Like it might do something totally different for a number, or there might not be an upper method for a number. But that's the basic idea. Len I can call on is just a general function, and upper is a property or a method of a string in this case. So if I run this code now with the dot syntax, let's ignore this because some leftover cruft, but this will uppercase my string, lowercases it, prints the string again to show you it's unchanged, and case fold, which I guess was expecting that to reverse the case, but it doesn't. I'm not sure why, but I'm not going to try to debug it right now. But there's something interesting happening here, which is that when I called name.upper, it didn't actually change this original string. It created a new string and returned this uppercase version of it. And the way we know that is because we printed name again down here, and it's still the original string that was as we first specified it in that very first statement. We'll come back to this, but it's important to know that strings typically don't get modified; they get copied and you get a new copy of them with the properties you want, and the old string is still around as in its original form. Find is an important string method to know about. It gives you the ability to sort of find substrings within a string. So whereas I said the in operator tells you is a substring in another string, this one says if this substring is in another string, where is it? I guess in theory, this is equivalent to in plus more value, because you can use find to tell whether something's in a string or not. But I find the code to be a lot more readable when I only want to know the Boolean yes or no, is it in the string or not. I find the in operator to be more readable. But in theory, find is sort of the superset of the end operator, and also this additional information, where in the string does the substring reside. Example here is bookkeeper, and I say where is the substring OOKKEE. And I like this example because bookkeeper is a special word in English. It's one of the only ones that has this pattern of 2 repeated consonants, then 2 more repeated, and then 2 more. So 3 pairs of repeated consonants. Anyway, if you run that find, it returns where in the original string that substring resides. And as we can see, it's right there, starting at offset 1. And so we get back a 1 from the find method. This is a method, and so we're calling it with Meister dot. We're not calling find and passing Meister to it. So it's not a function, it's a method. And if we call find with a substring that doesn't exist in the string we're calling it on, as it doesn't in this, we don't see OK anywhere in bookkeeper, we get -1 returned to us. And -1 is this function, this method's way of saying, sorry, that does not exist in the string you're operating on. And here's one more example. The string, just a single character K, appears twice, and find tells us the first location. So it's offset 3, 0, 1, 2, 3, and sure enough, there's a K. You might wonder what happens if I try to find the empty string, and I'm not actually sure. I think it's going to say 0 because the empty string is in every string, and so it's everywhere, or between every character and the beginning of the string and the end of the string, but I'm not sure. Let's see. Yeah, it says offset 0, so you can't see it, but there's an empty string right there between the open quote and the B. I'm kind of kidding about that, but that's sort of the way I think to think about it, or at least the way I think about it. I'd like to talk a little bit about string immutability. This is the idea that strings cannot change once created. We call this immutable or immutability, but that's really just a fancy word to say that it's unchanging. You can't change a string. And what does that mean? Didn't we just call name.upper and see that we changed a mixed case or a lowercase string to an uppercase string? Well, we sort of did, but what actually happened was we got a new string. So when you call something like this, name.upper, the upper method takes the name, the string that name points to, and it makes a copy of it, and it gives you back a copy with the desired characteristics. So now you have 2 strings. You have the original string, and you have the copy that is all uppercase that the upper method created. And we've saved each of them in 2 different variables, so we can then print them. We can say name still exists, and upper name is a new and different string. So let's try running that just to see that it works the way we think it would. Mark still exists. Mark is a new string. We can even set name equal to new here, and that will overwrite Mark. Actually, let's try this, make this a little bit more clear. We don't need all these prints. So this shows you that the original string is preserved and the new string is allocated, and they both live sort of in parallel. I could have actually said name equals here. And that sort of looks like, okay, maybe that changes the string, but it doesn't. It creates a new string, and it sets the variable name to point to the new string. Now, name is going to now be all uppercase, and upper name's not going to exist. So I'm going to get an error. Oh, no, upper name still exists because I just ran the cell a minute ago. But name now is all uppercase. What happened to this string? It's sort of gone because nothing points to it anymore. So Python cleans it up. But the key is it never got altered. Once I created that value, Python respected the fact that strings are immutable, and it never tried to actually change the content of that string. What I did here was I just simply overwrote what this variable name points to. So Worth knowing because it might seem like a technicality or something that's kind of obscure, but it's worth knowing because, as we'll see with these more advanced data types like lists and tuples, some of them are changeable and some of them are not, and it's important to know which are which. And it also dictates some rules like what kind of things you can use as key in a dictionary. And of course I haven't explained what a dictionary is, so just file this as something that's good to know about for later. There's another useful capability in strings, which is another string method that's quite useful, is the replace method. And so replace lets you say every occurrence of string A, replace it with string B. So in this example, I'm saying my salary is 1,000, not saying what unit or what time frame that is, but I want to say that I'd like to replace the zeros with 2 zeros, which seems like a nice thing to do. So if I run that, I change this back to 2 zeros. Suddenly my salary is 1,000,000 because every one of these 3 zeros got replaced by 2, so we now have a 1 with 6 zeros. Having the same character in both strings is a little confusing, so I'm going to try changing that to an X. And I'll run it again, and I get a 1 with 3 X's. So you get the idea. This could be anything. Either of these isn't restricted to a single character. So if I do this, change 3 zeros to an X, I get 1X. I can say X, Y, Z, blah, 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 and I get that. And if I just say replace the 0 with that, because there are 3 of these, I'm going to get 3 versions of that mess. So hopefully that's clear. It just gives you the ability to take any string and replace some arbitrary substring with some other substring. And you can even specify how many occurrences you want to replace. I think you do that with a third argument here. I'm going to say 1, and I should get the gobbledygook and then 2 zeros. Yeah, so that's if you don't specify the number of occurrences, it effectively tells this method, replace every occurrence in this string. And one important thing to highlight, and this is repetition, but I think it's important, is I said that this replaces the 0 in the string with this or that. It doesn't actually replace the values in the string. It makes a new string where the character sequence is altered according to your specifications. So when this salary comes back, it's replacing that original string. It's not really changing it. So hopefully, I'm probably overdoing that point, but hopefully that's clear. And here's another example. How am I doing is my input. I'm getting feedback, and I want to replace worst with best. This is probably pretty trivial given the examples we did before, but I just want to show you can interact with input from the end user. So if I said, you are the worst teacher ever, can't type, my replace statement changes it to you are the best teacher ever. Again, it allocates a brand new string, returns that, and stores it in better feedback. And because I used a different variable name, the original variable is still there. If I wanted to, I could print feedback, comma, better feedback, and see them both. Worst, and best. So that's it for strings. Hopefully that wasn't too boring, but I think it's good to lay those kind of foundational concepts down early in the class so that when we revisit them with the more advanced data types, you'll kind of feel that sense of familiarity, and it'll make sense to you. And that's one of the things I really like about Python is certain operations you'll see over and over again with different data types, and they just start to make sense because they do logical things in the cases where they vary between types. I'm going to take a quick break now before we move on to the next topic, which is loops. Okay, picking up where we left off, we're going to jump into loops. And before we get into the syntax, I want to sort of motivate why you should care about loops. And the way I'm going to do that is by starting with a very simple program. I want to write a Python program that prints the first 3 integers along with the square of each one. So the square is defined as a number multiplied by itself. So the square of 1 is 1, square of 2 is 2 times 2 or 4, square of 3 is 9. And so this program works nicely. I set a variable I equal to 1, and then I print I, comma, I times I. And I pretty much do the same thing 3 times, except I vary the value I set I to. So let's run that code. And we see that it works nicely. But there are 2 problems with this program. One is that it's tedious, right? If you, well, actually that's the second point. The first point is scalability. So if someone said to you, your program's fine, but I want you to do it for instead of the first 3, the first 1,000 integers, you would need to copy this code almost 1,000 times, 997 times. And you'd have to edit all of those I assignment values for every. So you're talking about adding almost 2,000 lines, because there's 2 each, and doing a whole bunch of editing. And if it's 10,000 or 100,000 or whatever, it just gets worse. And so scaling this is painful, and then maintaining it is painful in the sense that what if the actual task that you do for every number changes? Like what if someone said, instead of the square, I want the cube, or I want the value multiplied by itself 3 times or 4 times. Well, now if you've done all the work to set the I value to 1 through 1,000, at least that part is done. But now you have to go back to revisit every single one of those print statements and change it to the cube or a higher power, which is really painful and tedious and time consuming. And so that's where loops come into play. Loops give you the ability to automate repetition, essentially. The simplest and first loop I want to tell you about is called a while loop. And it's one way to express this kind of repetition in Python. The structure of a while loop looks like this. You say while condition, and you don't actually say condition literally. That's a placeholder for any Boolean value. And I'll give you more examples that I think will make this more concrete. And then you have a block of indented statements. And a block can be, just like with the if statement we visited earlier, that can be 1 or more statements, but the key is the statements that you want to be predicated on this condition all have to be indented, and all have to be indented to the same level in Python. So the way this works is the condition is checked at the beginning of this statement. If it's true, Python runs the block of indented statements, and then it sort of jumps back up to the top again and retests the condition. And that's why we call it a loop, because it kind of goes in a circle. If the condition is still true, it does the block again, it goes back up to the top, and just keeps going as long as the condition is true. Once it evaluates the condition to be false, it skips over the block and continues execution at the first statement after the entire while statement, including the block. So this isn't super clear because of those dots, but the triple dots was implying more statements in that block. But I'm going to just add a next statement. That's kind of weird. Let's put a real statement. Let's say print done with loop. And now after we've run this loop for a little while, when the condition is false, Python doesn't execute this block, and it continues at the next statement after the loop, which is this print statement. The one thing to know is that if the condition is initially false, so as the very first time this statement is seen, the condition is false, then as you probably would expect, the block is just skipped and Python just continues with the next statement after the loop. So the entire loop is sort of has no significance to the program. It's not executed. Talked about this, that we indent the body just like we do with if statements. And let's ask, when I is initialized to 0, what happens here? So let's walk through this together. I equals 0, while I is less than 3. Well, I is less than 3 because it's 0. So we're going to do this block of 2 statements. So we'll print 0, and we'll add 1. This is a shorthand for I equals I plus 1. So I plus equals 1 says, add 1 to what's in I and save that back into I. So at the conclusion of this statement, I will be increased to 1. We'll pop back up to the while loop, or the condition. We'll say, is I less than 3? I is now 1. Actually, we'll we'll do this down here. Let me keep going, and we'll add a little bit of annotation to the code down here. So I is now 1. We print 1, and then we increment I again. So I is now 2. Jump back up to the top of the loop. 2 is still less than 3, so we'll print 2, and we'll increment it to 3. Now I is 3. The third time through the loop, or after the third time through the loop, we've now gone through with I equal to 0, 1, and 2. The fourth time through the loop, I is equal to 3, and we're going to hit this condition. We're going to say, is I less than 3? I is now 3, which is not less than 3. So this condition for the first time is now false. So the while loop's going to say, this condition's false, that means I'm done with this loop. I'm going to skip these two parts of the block, or these two statements, the block part of the while loop, and continue the program at the next statement after the loop, which is this print I. So same code is here, but what I've done is I have, instead of printing I, which is going to be confusing because when I is 3, we're just going to get a 3, and so it's going to look like it was part of the loop. I added a little bit more code to say we are done, or a little bit more to that string, so you can clearly tell when it was in the loop and when it was out of the loop. In fact, let's make that more explicit here. In loop, comma, and we are done. So we should see in loop 0, in loop 1, in loop 2, and then we are done 3. Let's see if that works as expected, and it does. And now the question is, what would happen if I initialized I to 1, to 2, and to 3? And I'm going to let you try that yourself as an exercise. So, but I recommend you first see if you can figure out what the code's going to do before you do those, and then try them out and see if you got it right. That's a great way to learn, is to sort of see if you can predict what the computer or what Python thinks. This variable I here that we initialize and then we increment inside the loop and then we test it in the condition, it's often called a loop variable or a loop counter, because it sort of controls how many passes through the loop, and it also typically controls the condition, or the condition is typically a function of that loop counter. Another example here would be generating squares using a while loop. And the reason I kind of next go to this is because it's pretty much the solution to the problem we saw earlier, where we were repeating, you remember that pattern where we'd say I equals this, print it, and the square I equals that. Now we have a way to express this much more compactly and much more scalably. We can easily change the number of squares we print. In this case, we're starting small, I less than or equal to 3. Let's go back to 3 here, and let's run this. So we set I equal to 1. We loop as long as I is less than or equal to 3. We print the number in its square, and then we increment I and continue looping. And we get the exact same program, or exact same output that we got with the manual version, where we were enumerating every line of code. So this works. Is this an improvement? And it is, and the reason, the way to really see what's so great about this version, or what the advantages of this version over the last one is, as I mentioned earlier, what if someone comes to you and says, I want to do that 100 times or 1,000 times? Well, now I just changed that limit, and that's it. I don't have to change 100 lines of code or 1,000 lines of code. I just change one number, and I magically get the exact number of iterations. Sorry, that's the wrong code. Exact number of iterations I want. So that's pretty cool. That's how we can scale the code. It also, I think this is a repetition. It also makes it easier to maintain the code, because if we wanted to change what the code does, so like initially, let's say the version we saw, what I've been calling the manual version, we would set the limit to 3, and we were printing I squared, so I times I. And then we said, let's make the limit 1,000, and that works great in a loop now. We can scale it to just about any size we want within reason. But now let's say someone says to you, I want the behavior of the loop to change. Instead of squares, I want cubes, I times I, or in Python we might say I star star I, which is the exponentiation operator, if you remember that says raise I to the third power. We can just make that one change in the loop, and now we've changed the behavior of the program without having to edit 1,000 lines of code. So this is essentially why loops are important, and you'll see loops in just about every programming language. It makes it possible to repeat yourself more gracefully and more efficiently than if you had to, do everything one line at a time. Here's another version. This is actually repetitious. I'm skipping that. Here's a challenge for you. I'd like you to go through this short piece of code and see if you can figure out where the bugs are. There are at least 5 bugs in this snippet, and I'll leave it to you to see if you can find them. I will probably add the answer to these challenges later, but for this week I want you to have a shot at it without the answer. Next up, nested while loops. We've seen nested if statements, right? So those were if statements within if statements, and nested while loops are while loops within while loops. So if we consider this first while loop I equals 0, again we're testing I for a termination condition. Then we're setting, as part of the block, this entire sequence of statements is controlled by that I less than or equal to 3. So these are 1, 2, 3, 4, 5, 6 lines of code that are part of this while loop block. And the block contains a while loop itself with a different variable, j equal to 1. We test for j going up to 3, less than or equal to 3, and then we print I, a slash, and j, and we end the line with a tab because we want to keep going for all the values of I. Once we finish the I loop all 3 times through, once we do all 3 times through this j loop, we fall out of the inner loop and we do a print. That's just to get a new line to start over on the next line, and then we continue the outer loop. You'll see this terminology where you have a loop inside a loop, and people will refer to the inner loop as this and the outer loop as this part and the entire block. So what are we doing here? I like to think of I as sort of like a row and j as a column, particularly because we're jumping to the next line every time we start with a new value of I. But we move over to the right every time we have a new value of j. So it's kind of like an array or a matrix with a row and a column. And you can see that it sort of prints out that way as well. We have like row 1 stays consistent here. That's the I value. I should have printed out I equals, maybe I can do that. Let's see. I equal, whoops. I have to go to the code cell. So if you see this yourself and you try to edit it, that's actually text. You have to scroll down a little bit to the code cell. So I'm going to change this to I equals, I'm going to just concatenate I because I don't want a space there, and then I'll say j equals plus j, and let's try running that. And of course it doesn't work because I'm concatenating a string with an integer. So let's turn these into strings like this. And let's try to spell stir. And let's do the same with j. And let's throw a little white space in there so it's a bit more readable. And let's run that. And now you can see I is 1, 1, and 1 for the first row, and j, which again I think of as a column, is going 1, 2, 3. For the middle row, I is 2 all the way across, and j again iterates between 1 and 3, and likewise with the last row, I is 3 all the way across. So hopefully that gives you a sense of the notion of a while loop inside a while loop, and you can do lots of really interesting things, particularly hierarchical types of computations that way. You can have loops inside loops, kind of for as many dimensions as deeply as you want to go. Another thing you'll run into is infinite loops. This is a loop that doesn't ever end. This can be explicit by saying while true, or it can be a condition that just for one reason or another never evaluates to false. This is usually not done by design. It's usually a bug, but there are cases where you'll do this on purpose and you'll use another technique to exit the loop when it's the right time. An example would be this loop. Does this loop end? So you set I equal to 1 initially, and you say while I is less than or equal to 3, do a print. And you can sort of tell this is going to run forever because you're never modifying I. So the loop counter needs to change at some point in the body of the loop, or the conditions never. That's not strictly true. the condition, the things that affect the condition, one or more of them has to change in the loop. Otherwise, the condition's never gonna change. So this will run forever and in an undesirable way. So I'm not gonna try to run it in this notebook because it'll make it annoying and hard to cancel it. But I'd like you to think about this case. This starts I at 5, and instead of incrementing, it's decrementing. Takes 2 off, and the terminating condition of the loop is I not equal to 0. And let's make that I. You could also make that I greater than or equal to 0. So the loop is saying as long as this is positive, and we're subtracting 2 each time through the loop. So would this ever terminate? And think about the not equal to versus the less than or equal to in that example, and see if you can figure out what would happen in both of those cases. The way I like to debug infinite loops is to put a print statement in the loop. You might think that's just going to exacerbate the problem because now you're doing more stuff than you were doing before. But this will often give you some insight into what's happening inside the loop. So I'm not going to make this an infinite loop. I'm just going to, for illustration purposes, I'll make this a finite loop. But I'm going to run this. It starts I equal to 1 and n equal to 20. And the idea behind this snippet of code is to sum the digits from 1 through 20. So it starts kind of a accumulator called sum at 0. And then it iterates over this loop n times. As long as I is less than or equal to n, I starts at 1. And as long as it's less than or equal to 20, it keeps going. So it's going to do this loop for the first 20 integers from 1 through 20. And each time in the loop, the body is going to add the current value to sum. So it's going to add 1 to sum, and then 2, and then 3. And so it's basically adding up all the numbers from 1 to 20. And of course, it's incrementing the loop counter so that we eventually finish the loop. And at the very end, we're going to print the sum. So we'll run that, and we get sum of 1 to 20 is 210. And let's imagine something we got a wrong answer, or the loop was running forever and we had to interrupt it. The way I would try to debug that is just to add a simple print statement that says I is this and sum is that, and let's see what's actually happening. And by doing this, we can sort of peer inside the loop and see each time through that cycle what's actually happening to I and what's happening to sum. And we can see that when I is 2, it's sort of interesting. We don't see the case where I is 1, and that's because we put the print at the end of this block. Let's put the print at the beginning so we can sort of see the state before the body of the loop actually gets going. Let's run this, and we see, okay, the first time through the loop, I is 1 and sum is 0. That's what we would expect because those are the initial values. Second time through, I is 2 and sum is 1 because we added 1 to 0 and got 1. Third time through, sum is 3 because we added 2 to 1. Fourth time through, sum is 6 because we added 3 to 3, and so on all the way down to the 20th time. Sum is started with 190, and at the end of the block, we'll get 190 plus 20, which is 210, which is the final answer. So hopefully that's clear. It's a kind of a debugging technique I've been using for 40 years, and there are all sorts of fancy ways to debug code inside IDEs, and those are cool too. But this technique is simple, usually pretty effective and easy to use. So I recommend it, especially for beginners, for debugging problems in general. This program's illustrating getting some input, a starting integer, an ending integer, and an increment. So it's kind of parameterizing a while loop based on user input. And the question is this fail-safe? Will this always finish? Or is there some way you can make this program turn into an infinite loop? And so that's a challenge for you. Can you run this code and enter some input that makes it run forever? It's actually not too hard. I'll let you try to see if you can do that. The idea that I wanted to get across here is when you start making code depend on input from someone else, whether it's manually input interactively or whether it's reading something off of a disk file or something like that, you need to be careful that the data you read in is suitable for the computation you want to do, that it's not going to cause problems. And that typically means that it has the right type and it's in the right range, and things of that nature. And so you want to be careful about trusting input, making sure that you don't just assume the stuff coming into your program is sensible and meaningful. It's really good to write code that verifies that the stuff you're operating on, especially when you're taking input from other sources, makes sense and isn't going to cause your program to do something either wrong or run forever. This is a more robust version that does a little bit of input checking. It's probably the least checking you might want to do, just to keep the example very simple. But this is a theme you'll see as you write more and more real world software, is you need to kind of be careful and verify things or as you expected in various places in the code. Two more important things about loops, and this applies to both while loops, the kind of loops we've been working on, and the ones we're going to see in a minute, called for loops. Somewhere in the middle of the loop body or the block, you can have a break statement. And the break basically says exit the loop immediately. Don't go back up don't do the rest of the statements in the block if there are more. Don't jump back up to the condition. Just move on to the next statement following this loop. Now, it would be a little weird for that to just be there unadorned, because the loop would never do more than partial one execution through the loop. So typically these are done under certain conditions. So you'll see an if statement, and if a certain condition is true, break out of the loop. And this is a nice way of saying, get me out of here. I don't want to do this loop anymore. And we'll see examples of where that's useful. And you can try this next example yourself. So this is a deliberate infinite loop. It says while true, prompts for input of a positive number, positive integer, greater than 0. If the actual value received is greater than 0, break out of the loop. Otherwise, tell the user, sorry, that was bad input. You need to give me a positive integer, and it just continues on through the loop. And so this is going to run forever as long as the user refuses to give you acceptable input. But once they give you the input you're looking for, we'll hit this break statement and jump out of the loop. So try that out. Hopefully that's clear. Continue is an analog to break, except instead of exiting the loop, it says jump back to the top of the loop and start the whole loop over again. It's kind of like take it from the top. There are various uses for this. I'll let you take a look at this code and experiment with it. There's an interactive version of it right here. But the basic idea is, like break, you're going to predicate it on a particular condition. You're typically never going to have this by itself. But it's a way to say, things are in such a condition that I don't want to continue flowing through the block of this loop, but I want to continue iterating. So it just says jump back up to the condition. Don't do any more in this loop body for this particular iteration. The next important kind of loop is a for loop. So whereas while loops repeat the logic based on a condition, a Boolean condition being true or false, a for loop repeats program logic based on the contents of a sequence. Now, what does that mean? Typically, that means you've got some data and you want to run a loop for every element in that data. Now, the only sequence we've seen so far is a string, so we're going to use a string as an example, but in upcoming lessons, when we talk about other types of sequences, we'll often use this for loop to iterate through the members of these other sequences. So here's an example. Meister equals this is a test, and if you accept that strings are sequences of something, the things that they're sequences of are individual characters. So the first element in this string is a T, and then an H, and then an I, and so on. So if I say for I in Meister, that says I want to iterate a loop where this variable I takes on the succeeding elements of Meister, and I want to print the value of I each time through the loop. And as you probably would expect, it just prints each character one at a time. Now this variable char, what I've done here is I've printed count and I've incremented count, but that's entirely that's just sort of to give you a sense of what's happening, but that's entirely unnecessary for a for loop. And in fact, that's one of the advantages of a for loop, is you don't need any loop counter or any other supporting variable. There's nothing to initialize, there's nothing to increment, and there's nothing to test. So this makes the for loop quite terse and quite easy to read, I find. So I can have just 3 lines. In fact, I could embed this in the for loop like that. I mean, I wouldn't necessarily do that. I like having the indirection of a variable, but in theory I could do it like this, and in 2 lines I can accomplish what we were doing with 4 or 5 lines in the while loop. You'll notice I'm printing count here, which doesn't make sense anymore. The notebook remembers the last value of count was 6, but that's not really very meaningful. And if I ran this cell from fresh notebook, it would give me an error. So let's redo that to just print char. And with 2 lines, I get this list of all the elements. That the loop is guaranteed to only run for every element in this string. So I don't have to worry about when it starts, when it stops, and any of the sort of bookkeeping I had to do with the while loop. This variable could be anything. I can call it mark. That's probably not a great name for a loop variable, but if I really wanted to, I could do that. And it'll work just fine because that variable is just a placeholder for the different values as it travels through the loop. Now that's great for symbolic data like strings, but what if I want to do numerical data like the stuff we were doing earlier with the columns and the rows and that sort of stuff? And for loops can be adapted to be used with a sequence of numbers just like we did in while loops. So here's an example. We can say for I in and then a sequence of 1, 2, 3. And I haven't described this syntax with the parens. This is called a tuple, and we'll get to this in 1 or 2 lessons. But this is a basic data type in Python which defines a sequence of values. So I'm saying for 1, 2, and 3, I want to print the value I and the square of I. And it just does the same exact thing we've been doing in a few examples. But once again, no need to initialize anything, no need to increment anything, no need to test anything. The bad thing about this code is that I have to enumerate all the numbers I wanted to operate over. And again, I'm back to this. What if somebody changes here I'm doing 6 numbers. What if somebody changes that 6 to 1,000? Do I then have to do this for the rest of my afternoon, or is there some better way? And of course there is a better way. The better way is the range function, which gives you a way to dynamically specify ranges of values in Python. You'll call this function range with a start, an end, and an increment. If you leave off start, it's assumed to start at 0, just like with indexing. End is required, but the actual end is end minus 1. Again, just like indexing and slicing. So some of these rules, although they may seem quirky at first, are at least consistent and pervasive in Python. An increment is sort of the amount you want to jump through the range by. Let's leave that alone for now. By default, start is 0. The ending will be the actual last value will be n minus 1, and let's leave increment off for now because it's optional anyway, and typically that we'll want that to be 1, and that's exactly what the default is. So for I in range 1, 3, print those values, and let's comment this out for now. And that only does 1 and 2 because the range function, like indexes, only go to 1, the ending value minus 1. So let's go from 1 to 3, and we get this table of squares. 1 to 4 is what I should have said. We get the first 3 integers starting with 1 and their squares. Now if someone did the trick of saying I want 1,000 values in that table, we just change that one value and we get the table of squares all the way up to, in this case, 999. If we actually wanted 1,000, we would have the range go up to 1001, like that. If we leave off the first value and just say comma 1001, we have a syntax error. So how do we say, why am I listing start? I have to come back to that. I think that probably is an error here. I'm not sure why I called start optional. That doesn't actually make sense. But let's say we do a 0 here. It should at least start at 0, which it does, and goes through 1,000. Let's try the increment now. Let's say I want to go by 2s. So I should only be looking at the even numbers starting with 0. And you can tell by looking at these that that's what it did. But if we go up to the beginning, we see 0, 2, 4, 6, 8, etc. And their associated squares. So that's how to use for loops with numerical values. And one thing to know about is you might worry, well, is range actually returning all those values? Because if I actually used a very large, let's imagine I got rid of the increment and I went into the billions or trillions or something like that. Does that mean my program's going to end up calling range and getting back this humongous list of numbers that I then cycle through? Because that's going to cost a lot of memory, and eventually my program won't fit into the memory in my computer and it'll blow up. And the key thing to know here is range actually is a special type of variable that Python understands to give it the data it needs as it needs it. So it doesn't actually calculate the whole range and return it in one fell swoop. It's a special type called an object. And in fact, that was a bad idea. Let me bring this back down to a reasonable value. You can see the type of what the value that range returns is a class. And we haven't talked about classes yet, but it's a way to define a special type in Python. And so range is a type that sort of feeds the loop data as it's needed, just in time. And the result of that is you don't need to queue up in memory or save up the memory space for all the numbers, even if this is a trillion. You'll just get one at a time, or a small number at a time. And this is one of the things that makes Python efficient for iterating numerically. Range is great for for loops, which we've already been talking about. And as with nested while loops, you can have nested for loops as well. Here's an example where we do something similar to the previous code example with a for loop. This is creating a multiplication table, a 9x9 multiplication table, and we have along the top the one value, and the column on the left column, that's the other value, and we're multiplying these together. So 5 times 4 is 20, and we're just constructing this table by having iterating over 10 values with I, and then inside each iteration of I, we're iterating over 10 values of j. Take a look at that code and see if you can understand why it works. If you're not sure, put some extra print statements in there, comment some lines out, simplify it, copy it to a new cell, play around with it, and see if you can kind of get to the bottom of how it's doing what it's doing. That pretty much covers what I wanted to talk about in this lesson. I'm going to give you a quick preview of what we're going to be doing in the next lesson. The basic building block for creating more and more complicated chunks of software is called a function. And you've already seen these things when we call print and input and len and all these other things. But you can define your own functions. And so this is an example of a function I'm defining in this cell. Actually, let's look at it in the code cell. So I say def, that's shorthand for define, function name, and then in parentheses, the argument that I want to pass to the function. And what this function called fact is doing is its goal is to calculate the factorial of the past number. And if you haven't seen it before, factorial is the product of 1 all the way up to a given number. So factorial of 4 is 1 times 2 times 3 times 4. And so the way we're going to calculate this is consider fact, this variable, not the function, the variable. And probably this isn't a great practice. I shouldn't use the same name, but for a simple example like this, I'm going to leave it. I'm going to use this variable fact as kind of an accumulator of the product, the kind of growing product over each iteration. So because I'm going to keep multiplying, I want to use 1 because that's the identity value for multiplication. I don't want to use 0 there, or I'll multiply a 0 by a bunch of numbers and end up with a 0. So I start with 1, and then I use my for loop, and I use I as my loop variable, and I go through the range of 1 to n plus 1. Now, why do I have my last variable in range n plus 1? Because as we know, that means the range will go through 1 less than the end value. So I really want it to multiply 1 through n. So I specify n plus 1 to get that nth value in the range. And the body of the loop is just multiply the last value of fact by I and keep going. Fact star equals I is the same as saying fact equals fact times I. And if I run this, so if I run this code, let me comment this out. That doesn't actually, compute anything. It simply defines the function fact. So def doesn't run the function, it simply defines it. So now once I finish this code, Python understands there's a function called fact and what it needs to do when it's called, but it hasn't been called. If I uncomment this line, it's going to be called, and the way I call it is by specifying the function name and passing an argument. In this case, it'll be 5. We expect that to be 1 times 2, which is 2, times 3, which is 6, times 4, which is 24, times 5, which is 120. And that's the answer we get. These numbers blow up pretty quickly. If I do the factorial of 10, I get 3,628,800. So you can play around with that, but that's something we're going to dive into more deeply in our next lesson. I wanted to give you another example program using loops this time because that's sort of been a theme for today. So what this is doing is I've got a cell here that's mostly doing JavaScript code. So this line here, JS equals JavaScript, and then this long triple quoted string. This is a bunch of JavaScript, and you might be wondering, why is he showing me all this JavaScript code if this is a Python course? And the reason is I want to do something interactive in this notebook. I want to actually take a picture. And sometimes it's easier to do that in JavaScript because JavaScript is the language that the browser executes. And so I kind of want you to ignore this cell. It's a bunch of code that really is not relevant to what I'm trying to teach you, but it just happens to do something useful, which is activate my camera and let me take a picture. So I come down here. That's an old picture. Actually, what that cell does was simply define the function. So once again, you define a function, it's created, but it's not been run yet. This cell will actually run the function. Okay, so now we've got live video into this camera, and this capture button will capture a still. Let me center myself. And there I am. And now what I'm going to do is run let me get rid of this old output. What I'm going to do is print out the grayscale version of this, and then I'm going to iterate through all of the pixels in the image. And pixels are the little dots that the image is composed of. And you can think of these as an array or a grid of rows and columns, where each row-column pair is a set of coordinates that defines a location in this image. And there's a value at that coordinate that tells us what color, in this case a color image, that pixel should be. To simplify things, I'm converting it to a grayscale here, and I'm going to display the image. And then I'm going to go through a loop 5 times, and each time through the loop I'm going to visit the rows, and then inside that I'm going to visit the columns. So for each row I'm going to see all the columns one at a time, and then I'm going to go to the next row. So we're seeing actually a triple nested loop here. The inner 2 loops are visiting each pixel, each sort of row column location in the image. The outer loop is just kind of saying repeat this process a certain number of times, iteration times, and I'm setting it to 5 here. Okay, so I'm visiting every pixel in the image, and I'm doing the whole thing 5 times, but what am I doing when I visit each pixel? And that's where the inner loop's body is important. What this is doing is saying, I want to set the value of pixel ij to be the average of the pixels surrounding it. So I-1, j-1, I-1j, I-1, j+1, the 3 pixels above ij, ij-1, ij, and ij+1. Those are the 3 pixels around ij, horizontally, it's the one horizontally before and after, and ij itself. And then I+1, j-1, I+1j, and I+1, j+1. Those are the 3 pixels below ij, centered below ij. So I'm really saying, give me the sort of the neighborhood, the 9 pixels around ij, add them all together and divide by 9, which basically says, give me the average value of the surrounding 9 pixels, or surrounding 8 plus the pixel of interest. And then display the image again. And what this is going to do is just sort of blur the image, because it's averaging out everything. So let's take a look at that, run that cell. And again, I'm not expecting you to fully understand what's going on here. I just want you to get the general idea and just show you an example of nested for loops in practice. And there's the original, and there's the, I don't know how obvious it is to you that it's blurred, but let me blow it up a little bit. I think you can see that it's blurry. I'm going to change it from 5 to 10 and run it again, make it even blurrier. And I like this example because if you've ever used a program that has image filtering like Instagram or any of these popular apps that kind of do funny things with images, this is essentially what they're doing. They're taking the pixel data, the underlying row and column information behind the image, and they're visiting each pixel and modifying it in some fashion. So it's obviously they do more sophisticated things than this, but so this is the basic concept of what those image processing programs are doing. And here's my blurred image. This one going through 10 times makes it really blurry, so hopefully you can see that. Homework for this week is to read chapter 3 in our online book, make a copy of this notebook, and actually I would do that in different order. I would do the notebook first, I think. Yeah. I would copy the notebook and complete all the challenges, make sure you understand it, work your way through all of the cells I've just shown you. And then try the homework problems, which are below. I've got, I think, 5 this week. Yeah, 5 homework questions to try. And I would read chapter 3 when you get a chance of the online book. One other thing is, for the next class, I'd like you all to install your own copy of Python. And the reason for that is that the notebook environment we're using is a little bit artificial because it kind of sets everything up for you, which is great for beginners. But at some point in your adventure with Python, it'll be useful to have your own copy installed on your laptop or your desktop computer, whatever computer you're using. And so the way to do that is to visit this site and follow the instructions to download, and it should actually figure out what type of system you're on. Like I'm on a Mac, and it just figured that out and pops me up with a button that says download Python for Mac OS. If you have trouble with that, email me and we'll get you going. And I think that's it. Yeah, you'll see an exercise on palindromes here, and I've got an extra cell with some fun palindromes. But anyway, that's it for this week. Hope you enjoyed it, and we'll see you next week with lesson 4.